They land on a planet flooded with shallow water. The sky is quiet. Time seems normal, but when they return to the ship, 23 years have passed. In Interstellar, 1 hour on that planet equals over 2 decades for everyone else. It's a shocking moment, not just for Cooper, but for us watching. Because how can time just stretch like that? There were no spinning time machines, no magic portals, just a black hole nearby. So what exactly happened? Was this science fiction, or something physics truly allows? More disturbingly, if this is real, could we actually lose years of our life by simply being too close to something heavy? Einstein had a theory, but not even he lived long enough to see it tested like this. Let's walk through the logic and ask, is gravity really strong enough to slow time itself? The moment they step onto Miller's planet, it doesn't feel like an alien world. It feels like a trap. The surface is flat, drowned in knee-deep water that barely ripples. Skies painted in soft gray silence. Clouds don't move. Even sound feels slower, like someone turned the universe down to half speed. But there's something wrong, something you can't name, something you can feel. This is the place Interstellar warned us about, the one where 1 hour equals 7 years. But nothing looks dangerous. There are no whirlpools, no glowing anomalies, no screaming clocks, just silence and ticking, one tick every 1.25 seconds, like a heartbeat echoing through time itself, each one marking the passage of whole years elsewhere. They don't know it yet, but every step they take is aging someone else. Doyle dies in minutes. Brand nearly drowns. Cooper shouts orders that space can't carry fast enough. They run, they escape, they survive. But when they return to the ship, Romilly is not the same man. His hair grayer, his eyes hollowed out by loneliness. He's aged 23 years. And Cooper? He still has water dripping from his boots. It's one of the most quietly horrifying moments in science fiction history. Not because something exploded, but because time betrayed them. No machine did this. No villain. No paradox. Just a black hole. Just gravity. And here's where it gets even stranger. Cooper didn't feel anything. No stretching. No slowing. No strange vibrations. Because gravity doesn't need permission to bend time. It just does. And if a planet can sit close enough to a black hole to compress time, then time isn't what we thought. It's not fair. It's not equal. It's not even the same thing in every part of the universe. What Interstellar did in that one scene wasn't just science fiction. It wasn't exaggeration. It was a cinematic echo of one of physics' most terrifying truths. But here's the thing. We believe time is stable because we've never seen it change, but we've also never stood next to a black hole. So now the real question emerges. Can gravity really twist time like that? Not theoretically, not metaphorically, literally. And if so, is there any place in the universe where time nearly stops altogether? Because what's waiting near that answer is not just science. It's a very different understanding of reality itself. Time doesn't ask questions. It moves like breath, steady, invisible, always there. We live by it, age by it, build our memories on its rhythm. And somewhere deep in us, we believe it's fair. You and I could be on opposite ends of the earth. But if we start a stopwatch, let it tick for an hour and then meet again, we'd assume we lived through the same hour. Same tick, same world, same rules. That assumption is so deep it becomes invisible. We build clocks by it. We structure society by it. And when something challenges that idea, like in Interstellar, it doesn't just break a rule. It breaks something personal. Because how can time, this universal shared experience, treat people differently, based only on where they are? We don't feel time stretch or squeeze. Our bodies don't tingle when the seconds change shape. Even when we fly across time zones, it's the clocks that change, not time itself. So we cling to the belief that time is absolute, like a river that flows the same for all. But that river doesn't exist. And the illusion starts to crumble with one uncomfortable truth. Time is not the same for everyone. It never was. This isn't just theory. It's been measured, proven, observed. A clock placed at the top of a building ticks faster than one at the bottom. Not because it's faulty, but because it's higher, farther from the Earth's center of gravity. The difference is billionths of a second, yes, but it's real, repeatable, and irreversible. Now zoom out. What if you're not just a few meters higher, but near a black hole? Then the effect isn't billionths of a second, it's decades. Time doesn't flow uniformly across the universe. It flows based on something we can't see, the shape of space itself. The closer you are to gravity, the more space bends, and the more time bends with it. And yet, you'll never feel it. You won't hear time stretching. You won't feel the universe aging faster without you. You'll just blink, and the world will have changed. That's what makes time dangerous, not because it moves too fast, but because it moves differently, and never tells you when it does. And that idea that time could betray our senses wasn't born in a Hollywood studio. It was born in the mind of a man who questioned the most basic assumptions the universe gave us. A man who asked, what if time isn't what we think it is at all? His name, Einstein, and he didn't break time. He simply revealed how fragile our idea of it really is. Time was supposed to be simple, a constant beat in the background of the universe, unchanging, equal, reliable. But one man wasn't convinced. He wasn't in a lab. He wasn't a professor. He worked in a Swiss patent office, spending his days reviewing inventions he didn't invent. But in his mind, something was stirring. His name was Albert Einstein, and at just 26 years old, he did something that no university, no telescope, no textbook had done before. He broke time. Not with an explosion, not with math, but with a thought experiment. Imagine two people. One is standing still, the other is riding a train moving near the speed of light. A beam of light is emitted at the center of the train. For the passenger, it hits both ends at the same time, but for the person watching from outside, the train is moving, so light has to chase one wall and meet the other early. Same light, same event, but two different versions of when it happened. That was Einstein's key realization. If two events appear simultaneous to one person, they might not be for another, which means time is not absolute. It depends on your motion. That's not philosophy. That's the beginning of special relativity. And with it came the first blow to our shared idea of time. But Einstein wasn't done. 10 years later, in 1915, he published his even stranger theory, general relativity. Gravity, he said, is not a force. It's the bending of space and time around massive objects. Think of space-time like a fabric. Place something heavy, like a planet, on it, and it sags. Place a marble nearby, and it rolls inward. But what most people miss is this. When that fabric bends, so does time. Clocks tick slower, deeper in the curve, not because they're broken, because they're obeying the shape of space itself. Einstein's equations didn't just describe this. They predicted extremes, places where time could be stretched so thin it nearly freezes. But no one believed him, fully. He even wrote a letter saying he doubted black holes could physically exist. The math was too wild, too strange, too real, and yet his theory waited. In 1976, scientists flew atomic clocks in airplanes. The ones at high altitude ticked faster, just as Einstein predicted. In 2015, LIGO detected gravitational waves, ripples in space-time from colliding black holes. Another confirmation. And today, the GPS in your phone literally corrects itself every nanosecond to account for time moving faster 20,000 kilometers above Earth than it does where you're standing. Without relativity, your map wouldn't work. Einstein's thought experiment has now become a global utility. But if gravity bends time and black holes are the heaviest things in the universe, then what happens to time just outside their edge? Because Interstellar didn't exaggerate. It ran the math. And it may have gotten far closer to reality than most people realize. We've accepted it. Time can stretch. Gravity can bend it. And Interstellar wasn't lying. It was applying Einstein's math to a cinematic beach. But something still doesn't sit right. Something subtle. Something personal. If time really changed that much, if 1 hour became 23 years, why didn't Cooper feel it? There was no dizziness, no slowness, no strange shift in perception. He ran through water. He yelled. He fought to survive. Everything felt normal. But outside, entire lifetimes passed. That's what breaks the viewer's mind. Because when something changes that drastically, we expect to feel it. If a plane speeds up, you feel it in your chest. If a roller coaster drops, your body tells you. But time? Time betrays you silently. It doesn't alert you. It doesn't knock. You blink, and the universe moved on without you. And that is the true horror of Interstellar's scene. Not the wave, not the loss of years, but the fact that you'd never know it was happening until it was already over. That breaks more than just science. It breaks our emotional instinct. Because if someone can lose decades of their life simply by being in the wrong part of space, then what else don't we know we're missing? The contradiction deepens. If time slows near gravity, why do we feel nothing? Why doesn't a planet near a black hole feel slower? Why don't you notice clocks tick slower when you go into a valley or climb a mountain? Because the most disturbing truth is this: you always experience time as normal, no matter how distorted it actually is. Your brain cannot detect the curve of space-time it's inside. Your watch ticks, your cells divide, your thoughts form, and to you, nothing feels different. Because time dilation doesn't change how fast your clock ticks. It changes how your clock ticks compared to someone else's. This isn't time travel, it's time offset, and it's invisible. But now imagine this: two twins, one on Earth, one near a black hole. They each live 1 year. When they reunite, one has aged a year, the other has aged decades, and both are right. That's the paradox. Time doesn't care about fairness. It only cares about where and how you are. So even after Einstein, even after Interstellar, we're left with an unnerving question. If time moves differently depending on where we are, then where is time moving the slowest right now? Time doesn't just tick, it follows curves, and space isn't empty. It's something you can bend. That's the strange, elegant truth behind everything Einstein discovered. Imagine the universe not as a void, but as a giant, invisible fabric, like a stretched bedsheet pulled tight in all directions. That fabric is called space-time. Now, place a bowling ball on it. The sheet bends. That's what a planet or star does to space-time. It curves it. And here's the wild part. The deeper the curve, the slower time moves at that spot. That's not metaphor. That's not math poetry. That's been measured. Time doesn't resist. It simply obeys the terrain. A second passes differently at the top of a skyscraper than at its base. Your head ages faster than your feet by about 90 billionths of a second every year. You age unevenly. Every single day. You don't feel it, but physics does. Now crank the gravity up. Take a black hole. Not just massive, dense. A city's worth of mass squeezed into a point. A place where space-time isn't just curved, it's warped, twisted, collapsed, and just outside it, on the edge of no return, sits Miller's planet. At that distance from a black hole as massive as Gargantua, space-time is stretched so severely that time itself slows to 1/60,000th of Earth's rate. Let that sink in. For every 1 second on the planet, over 16 hours pass for someone watching from afar. That's not Hollywood. That's the math. And the math was real. Physicist Kip Thorne, who advised Interstellar, ran full simulations of how space-time would behave near a supermassive spinning black hole. Even the visuals of the glowing light bending around it were rendered using real physics equations, not CGI guesses. He didn't invent a theory for the movie. He applied a real one. And when he did, something happened that surprised even him. The visual effects team fed the physics into their render engine. And they discovered a lensing effect, the halo of light around the black hole that no one had ever visualized before. A movie image became a published scientific paper. But that raises a chilling question. If time slows near a black hole, could it ever stop completely? Could someone stand still in time while the universe ages around them? Because physics says, if you stand close enough and never cross the edge, you could live seconds while stars are born and die around you. We live like time is ours. We make plans, celebrate birthdays, count the hours until someone returns. But Interstellar shatters that illusion because time didn't move the same for everyone. Not in the galaxy, not on that ship, not between those who waited and those who landed. Cooper lost 23 years of his daughter's life in 61 minutes. Not because he failed, not because he chose wrong, but because gravity simply demanded it. He returned from the surface of Miller's planet, water still dripping from his suit, to find his crewmate gray-haired and hollowed out, to find the voice logs of a daughter who had grown older than he was. And that's when the science stops being theoretical, because time dilation isn't just a plot twist. It's emotional distortion. It raises questions that no equation can comfort. What is a relationship when time itself is not shared? What happens to love when memory travels at different speeds? Einstein once said, "For us believing physicists, the distinction between past, present, and future is only a stubborn illusion." He was right, but what he didn't say is how deeply we need that illusion. We want time to feel equal. We want shared moments to mean the same thing for everyone involved. But physics tells us that even if we hold hands, if our paths diverge through space, our clocks may never agree again. That's terrifying. And it's beautiful, because it means time isn't something happening to you. It's something you're carving through with every step, every choice, every position in the universe. You don't just live in time, you shape the kind of time you live. And that means something profound. You and I are not in the same timeline. Not exactly, not ever. And yet, we still try to connect. We still speak across those curved dimensions, trying to hold on to meaning, memory, love, through letters, signals, even silence. Maybe that's what makes us human. Not that we obey time, but that we try to share it anyway. It's rare for a science fiction film to respect physics. Movies bend rules, that's what they do. They're not textbooks, they're dreams. But Interstellar did something bold. It didn't just consult a physicist. It let one of the most respected minds in gravitational theory, as Kip Thorne, guide the science from the inside out. He set a condition before agreeing to help. No violations of known physical laws. So what the film showed had to be possible. And here's the shocking part. It was. Let's start with the hardest thing to believe, in Miller's planet. Could 1 hour near a black hole really equal 7 years in orbit? In short, yes, but only under extremely specific conditions. The black hole would need to be supermassive, around 100 million times the mass of our sun, rapidly spinning, close to the maximum allowed by physics, precisely configured so that the planet could orbit close without falling in. This kind of black hole is called a Kerr black hole. And the math behind it isn't just theory, it's been studied for decades. In Kip Thorne's calculations, such a setup could slow time to the degree the film describes. He even confirmed the 1 hour 7 years ratio under these conditions. The gravity near the event horizon stretches time by a factor of 60,000. But now, the bending, that incredible ring of light around Gargantua, like a glowing eye around shadow, wasn't an artistic invention. It was generated using real gravitational lensing equations. Light passing near a black hole bends so severely that it can loop around it multiple times and still reach the observer. In fact, the glare and distortion were so intense in the raw render that the team had to tone it down. Otherwise, audiences wouldn't believe it was real. They weren't exaggerating. They were holding back, but not everything was perfect. Let's talk waves. The towering wave on Miller's planet, hundreds of meters high, was a creative guess. The idea was this: near a black hole, gravitational gradients could stretch tides into massive, slow-moving giants. But realistically, the presence of an ocean that's shallow and a planet that's stable that close to a black hole raises several problems. A planet that close might be ripped apart by tidal forces or its atmosphere stripped. So while the time dilation is accurate, the habitable conditions may be less so. And yet the filmmakers knew this. They made trade-offs because Interstellar wasn't a physics lecture. It was a what-if scenario rooted in the best science we have. They didn't claim this world was likely. They asked if it was possible. And physics, surprisingly, said yes, because sometimes when art respects science, you don't need to break the rules to show something unbelievable. You just need to follow them all the way to the edge. So, can gravity really slow time? Not just in theory, not just in CGI, yes, and not by seconds, but by years. If you get close enough to something massive enough, time bends, and it bends in silence. That's what Interstellar got so right. It didn't make gravity stronger than it is. It made us more aware of what it's truly capable of, because what we call gravity isn't a pull. It's a shape, a bend in the floor beneath space and time itself. We don't fall. We follow curves. And when those curves become steep, time becomes uneven. Cooper didn't feel the weight of 23 years because gravity didn't press him. It redefined what a second meant to him. That's not just science fiction. It's something our GPS satellites already correct for, every single day. Without relativistic adjustments, your phone's location would be off by kilometers in minutes. Time is flexible, but not random. It follows the mass and motion of everything around it. And when that mass becomes extreme, as like a black hole, time isn't just stretched, it's twisted. So what does that mean for us? It means we're not all moving through the same universe in the same way. Your experience of time might be subtly different from mine. Your future might not tick forward the way you think it will, and that opens a haunting question. If gravity can slow time, then is there a place in the universe where time has nearly stopped completely? A frozen pocket of now? A place where, right this second, time is still ticking through a moment that, for us, happened millions of years ago? And if that's possible, then what else have we misunderstood? Maybe time was never the steady river we imagined. Maybe it's a landscape, and we're just moving through it, on paths curved by things we'll never see, but always feel. Maybe time isn't what separates us. Maybe it's what connects us through gravity, memory, and mystery.